Okay, so we're now going to talk about solving linear quadratic systems graphically. If you remember from doing linear systems, you're looking for where these two graphs intersect each other. Now it's going to be, instead of two lines, it's going to be a parabola and a line. So my first question is, how many solutions can a linear quadratic system have? Well, it depends on how many times they intersect. Most of the time, you're probably going to have a parabola and a line that intersect at 2 points. And again, remember, the solutions are the actual coordinate pairs for those intersections. It is also possible that you could have a parabola and a line that only intersect at 1 point, okay, in which case you'll just get one x and one y that actually make a coordinate pair where they intersect. And it's also possible that you could have a parabola and a line that don't intersect at all, okay, so that would be 0 points, and that would be the kind of problem where we would say we have no solution. There's no intersection of those two graphs. So when you're doing this, you just literally have to graph the parabola and the line on the same grid and see where they intersect each other. So let's start with y equals 3x minus 1. Okay, knowing what we know about y equals mx plus b form, this means we have a slope of 3, make it 3 over 1, that's your rise over your run. Okay, and I have a b value of -1, so that means I'm starting at the point 0, -1. So I start at the point 0, -1. I'm going to use this rise over this run to go up 1, 2, 3 over 1, up 1, 2, 3 over 1. Maybe I'll do one more, 1, 2, 3 over 1. And that is my linear graph. Okay, so make sure you use a straight edge, especially when you're trying to intersect things. You want to make sure you're graphing them properly. It's also probably good to label them because you're graphing two graphs on the same grid. The next thing I want to do is I want to graph that parabola. So just like I had said in our graphing quadratics lesson, the best way you could do it is to graph -x squared plus 4x plus 1 in your calculator and take a look at the table. You're looking for where the values in the table start to repeat. So I can see that right here as I go from 0 to 4. Let's see if graphing those points are enough to get all of the points of intersection. That's the thing, you have to make sure you get all of the points of intersection of these two graphs. So I'm going to start at 0, 1, okay, and then 1, 4, okay, and then 2, 5, there's that one intersection, okay, and then I have 3, 4, and I have 4, 1. So now the thing is that as I start to connect these parts of my parabola, I can clearly see one intersection, and hopefully you understand that there's another intersection over here, so I'm going to have to be careful and graph a couple more points here so I can actually get that clear second intersection. So I'm going to work my way up my table. -1, -4, and there we go. There's that last intersection. Okay, that's our parabola, y equals -x squared plus 4x plus 1. And remember, all of this graphing work means nothing without the solution. The solution is the points of intersection. So I'd like you to write the word solution, and then you're going to write those coordinate pairs. -1, -4, and 2, 5. Okay? And that is your solution for this. So now we go on to the next example. Pretty much going to be the same thing. Okay, so I'm going to start with graphing that line y equals -1. Y equals 0x minus 1 might make it a little easier for you. This tells you have a slope of 0. Remember, the 0 slope is that horizontal slope. Okay, so it's going to be horizontal. It's going to go through the b value of -1, so the point 0, -1. So here's 0, -1. I can plot a couple of points that go horizontal. And there's that line y equals -1. Okay, not to be confused with the x-axis, by the way. Then for my parabola, same as always, go to y equals, plug in the function, y equals x squared minus 4x plus 3, and take a look at your table of values. Look for where the values start to repeat. So you can see right here, I have 0, 3, I have 1, 0, I have 2, -1, 3, 0, and 4, 3. As I connect that parabola, you'll see that this is one of those situations where the parabola, I should probably be labeling, the parabola and the line only intersect at 1 point. And once again, all this graphing means nothing if you don't write out what the solution is. So the solution is the point 2 comma negative 1. By the way, if you ever wanted to check yourself, take this x and y, plug it into each of these equations, and make sure that both of them come out to be true, because that's what you're doing when you're solving a system. All right, last but not least, I have y equals x squared plus 3, and I have this weird looking second equation. I'm going to have to rearrange that to get that to y equals mx plus b form so that I can properly graph that. So x minus 2y equals 2. Okay, as y equals mx plus b. So I'll minus x from both sides. This gives me negative 2y. I'm going to put it as negative x plus 2, so eventually the x part will come first. Divide everything by negative 2, and I mean every single part of this. So I have y equals 1/2 x minus 1. Okay, so negative 1 over negative 2 would reduce to be a positive 1/2, and 2 over negative 2 would be negative 1. So I now know that my slope is 1/2. That's my rise over my run, and my b value is negative 1. So I start at negative 1, go up 1 over 2, up 1 over 2, up 1 over 2, get a couple of those points. Okay, again, use a straight edge to make a nice graph here to connect them. Okay, so y equals, actually I'll just do it, 1/2 x minus 1. I probably should be labeling with the original equation, but that's okay. Y equals x squared plus 3. So I'll go to y equals, type in x squared plus 3, take a look at my table. So again, you're looking for where the values repeat. So I see right here, I'm at negative 2 comma 7, so it's 4, 5, 6, 7, negative 1 comma 4, 0 comma 3, 1 comma 4, 2 comma 7. You'll notice in this case, my parabola and my line are not intersecting at all. Because there are no intersections, this would be a situation where we would say there is no solution. Now keep in mind, any of the graphs that I just did in these examples, I can graph them right in my calculator. So as long as I get this to be y equals 1/2 x minus 1, and I could take a look at the graph, and let's say that the problem just asked me like how many times do these graphs intersect. So all I have to do, plug them both in my calculator and see how many times do they intersect, and if I need the actual intersections, that's when I go and I really graph them and find where they intersect each other. Okay. So when it comes to solving linear systems of equations, which is basically two linear equations that you're trying to figure out where they're intersecting, you have 3 different types of ways that you could do this solution. You can solve by graphing, which I'll primarily do in the calculator because I don't think you really need to do it by hand right now. You can do it by substitution. Substitution will be good for an example where you have like one of your equations saying x equals or y equals. I mean, truthfully, you probably could have done the ones that I have for graphing using substitution because you have something that says x equals or y equals right away. And then finally, when you have all your x's, your y's, your equals, and your regular numbers lined up, then elimination is probably the best method. And I want you to pay attention to elimination because when we get to 3 variable systems, this is the kind that I'm going to end up using for those 3 variable systems. So start by graphing. This is the general idea of what you're doing when you're solving a system. You go to y equals in your calculator, you type in the 2 functions that you're trying to figure out where they are intersecting. Oops, negative 5x minus 2. Okay, so I take a look at the graph. So as I take a look in my calculator, I might be able to kind of count where the boxes are. This looks to me like it's maybe like negative 2 comma 3, negative 2 comma 4. Let's talk about using the calculator to actually find the intersection, because there are types of problems where it might not be linear equations, but you're going to have to find where 2 graphs intersect. So to be able to do that, you're going to use the trace menu that's called calc right above it. So second, trace, intersect. Okay, it's going to ask you first curve, second curve. You've only typed in 2 functions, so you're going to hit enter and enter. And then where it has a guess, you pretty much just have to have it closer to one point than another. There's only one point of intersection in this problem, so I hit enter, and it tells me that my intersection is the point negative 1 comma 3. What I'm finding is the x and y value that simultaneously solve both of these equations at the same time. In other words, the point of intersection of these 2 functions. Okay? Let's take a look at the second example. So again, we're trying to look out for where these graphs are intersecting. If you take a look at what's happening in the second one, and maybe before I even start typing in what this graph looks like, notice that both of these lines are going to have the same slope. Can you think about what that means? All right, so here's the line 2x minus 1. Here's the line 2x minus 4. What you are seeing is that because these have the same slope, these lines are parallel. And because these are parallel lines, they are never going to intersect. In other words, there is no solution to this particular problem. Okay, so your options are a single point of intersection, no solution if you're dealing with parallel lines, or if it turns out that your equations are actually the exact same line twice, so y equals 2x minus 1 and y equals 2x minus 1, then the answer would actually be infinite solutions, but that's a little bit more rare to come up. No solution is even pretty rare to come up. Most of the time you're going to be finding an x and a y coordinate pair that actually solves for where those are intersecting. So we get into situations where we could use substitution. Again, why I think this is better for substitution than, let's say, graphing, I'd have to rearrange this to y equals mx plus b form before I can graph it. My x's and y's are not all lined up. I have one of my equations saying x equals already. So what we're going to do in this problem is we're going to take the expression that we have for x and we're going to replace it in place of x in the other equation. So I'm going to rewrite that other equation. Y minus 2. In place of x, I'm going to put in parentheses 12 minus 3y equals negative 3. So now what I've done by substituting this expression into the other equation, now I have an equation that I can solve for just y or just x, in this case just y. So I distribute negative 2 inside the parentheses, y minus 24, negative 2 times negative 3 is positive 6y equals negative 3. Combine like terms on the same side, so I get 7y minus 24 equals negative 3. As I add 24 to both sides, I get 7y equals 21. When I divide both sides by 7, y equals 3. Now it's important that you remember that you are not finished when you've solved for y. You've got to get the entire coordinate pair, so I have to take my y, plug it back in, and solve for x. It's your choice which one you want to plug back into. I'll probably plug into the second equation because that will directly get me to the point where I have x equals something. So 12 minus 3y, I replace y with the 3 we just solved for. So I get x equals 12 minus 9, and that comes out to be x equals 3, and therefore my solution is the point 3, 3. Okay, again, your whole goal is to find the point where these two lines intersect. So now if I have a situation where I don't have x equals already, I don't have my equations in y equals form, but I do have the x's, the y's, and the numbers lined up, then elimination is going to be the best method for this situation. So what's going to happen is you're going to want to get either your x's or your y's to have the same coefficient with opposite signs. What's nice is that in the first example, I already have that. I have positive 3y and negative 3y. Because they are the same number with opposite signs, I'm going to go right to adding these equations together, and you'll notice that as I add them, this comes out to be 4x, the 3y and the negative 3y are eliminated, hence why it's called elimination, and then 9 plus 3 comes out to be 12, so I can easily now solve for x. And then all I have to do is, just like the last problem, plug back into one of my equations to solve for y. It literally doesn't matter which one you plug into, so I'll plug into the first one. So I have 2x plus 3y equals 9. I'm replacing x with the 3 we just solved for. So this comes out to be 6 plus 3y equals 9. When I minus 6 from both sides, 3y equals 3. And when I divide, I get y equals 1. Very important that when you make your coordinate pair, it's actually in the correct order. Remember that points are in the order x, y. In the previous example, they were both 3, so it didn't matter, but here it does matter. 3 is my x, y is my 1, and there's my solution to where those two lines intersect. Now, in case it ever happens that I don't have the same coefficient with opposite signs, what I'll have to do is multiply one or both of my equations to get there. So I'd say if you take a look at this one, it wouldn't be too hard to get the x's the same or the y's the same. I'm going to get the x's the same this time just to show you a different way of doing this one. So to do that, I need to turn the coefficient of x into a negative 2. So I can multiply that whole second equation by negative 2. I'm going to keep the first equation exactly the same, 2x minus y equals 4. And as I distribute, I need to make sure I distribute to every part of that second equation. So this becomes negative 2x, negative 6y equals negative 18. Be especially careful to remember to do the right-hand side as well as the variables. And now I go back to doing exactly what we did in the previous problem. Add my equations together. as I do this, the 2x's will be eliminated because they add up to be 0. Negative y plus a negative 6y adds up to negative 7y, and negative 18 plus 4 is negative 14. As I divide both sides by negative 7, this gives me y equals 2. Now I take that y equals 2, plug back into either of the original equations, so I'll just plug into the first one just to pick one. I'm replacing y with 2, add 2 to both sides. This gives me 2x equals 6, and then I finish up with x equals 3. As I said before, make sure you're stating them in the correct order. X comma y is always how you do a coordinate pair, so 3 comma 2, and there's your final answer. All right, so we are now going to get into solving 3 variable systems of equations, and we're going to use that method of elimination that we're using at the end of the linear systems of equations lesson. So it is going to be a little lengthy of an explanation, but I will tell you that it's one of those things that if you practice it maybe 2 or 3 times, it isn't too difficult. It's just a matter of practicing it so you know the steps. So the way that elimination works is that you're going to think about having these 3 equations. So I like to label them 1, 2, and 3. And the first thing I need to do is I need to basically pair up 2 of these equations twice. So I can pair up 1 and 2, or 2 and 3, or 1 and 3. What you're trying to do is pair them up and then cancel out the same variable from each pair. Okay, so let me start with pairing up maybe like 1 and 2. Okay, so as I take a look, 1 and 2. So I copy those over. I have negative x minus 5y minus 5z equals 2. And I have 4x minus 5y plus 4z equals 19. All right, so as I take a look at this, I can see that I already have the same coefficient on the y's. They're just not opposite signs yet. And if you notice that in the other problems, I have already actually the same number in front of the y, some of them already having opposite signs. So that means that I'm most likely going to want to be canceling out the y's. So whatever way I pair up my first 2 equations and whatever way I pair up my second 2 equations, I always want to be canceling out the same variable. All right, so in this situation, I'm going to multiply my first equation by negative 1 because I need to get that to be 5y and negative 5y so that they actually eliminate each other. I'm distributing this negative to each of those terms. This comes out to be x, a positive 5y, a positive 5z, and a negative 2. You have to be super careful with your signs in these problems. It's very easy to make mistakes. I'm going to bring over the second equation, 4x minus 5y plus 4z equals 19. Okay, once I've gotten it so that my y variables, because that's what I've chosen to eliminate, have the same variable with opposite signs, I'm now going to add my equations together. Those 5y's will cancel, so you've eliminated y. Okay, I add up. I have x plus 4x comes out to be 5x. 5z plus 4z is 9z. And 19 take away 2 is 17. I'm going to put a little star on this equation because we're going to come back to these starred equations in just a second, and we're going to do something with that a little bit later. So I need to pair 2 more equations together, so this time maybe I'll pair 2 and 3. Again, it doesn't really make a difference. I could have done 1 and 2, 2 and 3, 1 and 3, whatever's easiest. So as I pair together 2 and 3, I'm going to have 4x minus 5y plus 4z equals 19. And x plus 5y minus z equals negative 20. Okay, as I add these equations together, and by the way, I can go right to adding them because I notice that I have negative 5y and positive 5y. Whatever variable I canceled out in the first one, I have to be canceling out again in the second one. So you'll notice in this question, the 5y's I can go right to canceling out as I add these equations together. 4x plus x is 5x. 4z minus z is plus 3z, and negative 19 minus 20 comes out to be negative 1. That's my second starred equation. Okay, so now what you're going to do, now that you've eliminated y from each of those equations, is you're going to pull together your starred equations, and you're going to turn them into a 2-variable system of equations. So I have 5x plus 9z equals 17, and I have 5x plus 3z equals negative 1. Okay, so again, I'm going to pretend like I didn't have any of this stuff and just focus on this 2-variable system. Everything's already lined up, so elimination is probably the way to go for this. Unfortunately, I don't have the same number in front of my x or my same number in front of my z, so you have to multiply to get it so that one of my variables is going to cancel out. I'm going to multiply the second equation by -1 because I think that's the easiest way to get these to be the same. So this gives me 5x plus 9z equals 17. And then that second one, make sure you distribute negative to each of those terms, becomes -5x, -3z, and +1. Okay, so I continue with my idea of elimination. I'm going to add up those x's so they cancel out. That's again why we're using elimination. 9z minus 3z comes out to be 6z. 17 plus 1 is 18. And now I actually can get the value for z. Z comes out to be 3. So there's one part of my solution. Okay, so now that you take your z equals 3, plug back into either one of your starred equations. I'll just plug into this one because it's right here. And what you're going to be plugging in is this z equals 3. So I have 5x plus 3 times 3 equals -1. So 5x plus 9 equals -1. If I minus 9 from both sides, this gives me 5x equals -10. And if I divide both sides by 5, I get x equals -2. Last but not least, take the x and the z, plug it back into any of the original equations, and solve for your last variable, which will be y. So I'll just plug into the last one because it seems like there's less negatives there. So x, move this up a little. So I have x plus 5y minus z equals -20. Okay, so x is -2. 5y is what I'm solving for, minus z, which is 3, equals -20. Combine like terms, so that's 5y minus 5 equals -20, plus 5 to both sides. 5y equals -15, and when I divide by 5, I get y equals -3. So my solution, and again make sure you state it in the correct order, is x, comma y, comma z. Okay. I understand how that feels really overwhelming. So I'm going to actually show you an alternative method to be able to take the information that I have right here and solve it in my calculator. So that way, if it ever came up, like let's say on the Regents or something, you could be able to use your calculator to solve this question instead of doing the whole thing out by hand. So what we're going to use is we're going to use matrices in our calculator. So the first things first, I have to go to second matrix. Okay, so look at that button underneath math. We're going to go over to where it says edit, and we're going to enter in this matrix the coefficients of the examples we are working with. So my coefficients are -1, -5, -5, and 2. Then my next one is 4, -5, 4, and 19. 1, 5, -1, and -20. Okay, so maybe in terms of showing some work, and I'll use this space a little later for example number 2. This is the matrix that you're going to start out with. Okay, again, it's the coefficients of the example of the equations that you were provided with. Okay, and it's important, by the way, that you have all your x's, all your y's, your z, and your numbers all lined up before you complete this process. So I've entered this matrix in my calculator. Now I'm going to hit second quit to get out of the matrix and go back into the matrix menu. So second matrix, this time I'm going over to math, and you're going to scroll up from the bottom and do RREF. So that's the letter B, RREF. Okay, now you have to tell the calculator what do you want to do RREF to. You're going to do RREF to the matrix we just typed in our values. So I go second matrix, and this time now I select matrix A where I've entered all of the data that I just pulled from those equations, and when I hit enter, I'm going to get a solution that looks something like this: 1, 0, 0, -2, 0, 1, 0, -3, 0, 0, 1, 3. Okay, so what does this tell you? As you read down here, this says 1x is equal to -2, 1y is equal to -3, 1z is equal to 3, so it tells you that your solution is the point 2, -3, sorry, -2, -3, 3, just like we got when we solved it by hand. So I would say, and think in terms of getting the correct answer, I think you're better off using the matrices to be able to solve these questions. So to repeat this process for question number 2, I'm not going to do the whole thing by hand again. If you need to see it done again, just rewind and watch the video once more. So I'm going to take the matrix that I get from the coefficients of these problems. So this would be 1, 1, 1, 3, 2, 1, 1, 5, and 1, 2, negative 1, 4. Okay, I'm going to enter that into my matrix. So second matrix, go to edit. Okay, enter in that information. 1, 1, 1, 3. Okay, as I start to enter this, I just want to remind you that your calculator is only as good as the information that you put into it. If you type in the wrong information, it is going to give you the wrong answer. So you've entered in your data. You're going to go to do matrix operations. So second matrix, go to math, go to BRREF. Tell the calculator what matrix you want to do this operation to. So you pull up matrix A, and when you get that diagonal that looks like 1, 0, 0 and the number, 0, 1, 0 and a number, 0, 0, 1 and a number, then you know you've definitely gotten a solution for that. This right here tells you your solution is the point 2, 1, 0, and if you were specifically asked, like, what's the value of z? Z is the third one right here. Z is 0, or y is 1, or x is 2, and now you've solved that 3-variable system of equations.